All right, so welcome to the AutoGluon tutorial. We have a cool team of Amazon researchers here to give this tutorial. Will be split in three parts, basically. So apparently Nick will start. Nick is Senior Applied Scientist at Amazon AI and joined Amazon AI already in 2019 and is lead developer of AutoGluon, a tool we get to know here in more depth, but probably have already heard of. Then we have Oleksandr Shchur, also working on AutoGluon, is applied scientist at AWS, and in particular works on AutoGluon for time series data, just like Shchur Turkmen, who is a senior applied scientist at AWS and joined also the AutoGluon team in 2022. And with that, and with no further ado, I hand over to you and have fun.
Awesome. Thank you for the introduction. So super excited to be here again at the AutoML conference. So I was at the past two AutoML conferences where we also gave talks on AutoGluon and, kind of showcasing the evolution year over year as we add more and more functionality and further refine our system. So let's get into things. Okay, cool. So this is going to be in three parts. I'm going to start off with an overview of AutoGluon, as well as a highlight on AutoGluon Tabular 1.0. And then we're going to talk about Chronos, our foundation model for time series data, and also going deep into AutoGluon time series with Oleksandr Shchur. And then also we're going to talk about AutoGluon Assistant and kind of the future of no-code AutoML with Shchur. And then we're going to have a Q&A. We'll also have a Q&A as we transition between the sections too. All right. So ML in a nutshell. I like to think of machine learning in very simple terms because generally when customers use machine learning and automated machine learning, they don't really have like a very in-depth understanding of all the different techniques. So really, you bring your data, tabular, text, images, whatever, time series, you throw it into something, and then you get predictions out of that thing on new data, basically. And this is what drives basically value for the customer, the user, et cetera. And so this is like the core experience you kind of want to revolve around, at least if you're talking about supervised learning. And so you want an interface that kind of makes this as easy as possible. So I consider there to be 7 very important steps to have an AutoML revolution, where basically AutoML becomes the golden standard tool to use in most situations when you're doing machine learning. One, it needs to be easy to use. It needs to have strong performance. Basically, it needs to be pretty hard to just beat it through non-AutoML means, or basically it's not worthwhile to go and try doing it with non-AutoML means in most situations. It needs to have fast inference speed. Basically, you can't just be sitting there waiting forever for you to get your results from it. It needs to be stable and reliable, so basically it doesn't crash. It needs to be insightful. Basically, like the logging needs to make sense. You need to be able to debug it if things go wrong, things like that. It needs to be customizable. Basically, if you're an enthusiast user or you have some special circumstance, you shouldn't need to have to throw the whole AutoML framework out the window and start from scratch. You should be able to build upon what that AutoML system has created and add your little component to it that does what you need. And finally, it needs to be deployable. Basically, you need to be able to use this thing in the scenarios where your data lives and where basically you're trying to solve your problems. So for example, living on an endpoint or even on like hardware devices and things like that. And basically, if you can satisfy all 7 of these steps, I think that will herald the AutoML revolution. Basically, AutoML should become the thing that people use to solve machine learning problems. So I'm going to talk today about AutoGluon and how I think we've solved all 7 of these steps. So AutoGluon is an AutoML toolkit that democratizes machine learning. It is fully open source, Apache 2 licensed. It focuses on fast and accurate machine learning in 3 lines of code. It supports tabular, time series, image, text, and multimodal data. and it's open source and easy to install. Just pip install AutoGluon. And yeah, again, you can find us on GitHub, AutoGluon/AutoGluon. We have over 5 million downloads and over 8,000 GitHub stars. So AutoGluon is adopted by Amazon's Machine Learning University as the primary toolkit used to teach over 26,000 Amazon software development engineers machine learning. It's also deployed in over 800 Amazon projects internally, as well as being the backend for multiple AWS services such as SageMaker, Autopilot, and Canvas. It's used by over 200 companies, including NVIDIA, Intel, Capcom, Mitsubishi, Oracle, Pinterest, and many more. And we also had tutorials and keynotes at KDD 2022, a couple at NeurIPS and ICML and AutoML conference. All right, so there we go. So prior work in automated machine learning, so this is going back to like 2019 or so, was primarily focused on the model plus hyperparameter selection problem, or the cache problem. AutoGluon was very different in that it completely avoided doing any HPO whatsoever, and instead focused on strategies that win predictions contests on sites like Kaggle through prioritizing thoughtful data preprocessing, and especially model ensembling via multi-layer stacking. And then there's a lot of little details and tricks and optimizations, and basically those add up over time, and AutoGluon tries to incorporate as many of those as possible in itself. And as of today, in the latest large-scale benchmark paper on automated machine learning, the OpenML AutoML Benchmark 2024, it achieves the state-of-the-art result, achieving the highest average or the best average rank of all AutoML systems. So today I'm going to be focusing on AutoGluon Tabular for my section. The Netflix prize was one of the original, like very large scale tabular competitions that had $1 million prize pool. I've already talked about this before in previous talks. So basically, the solution was more models working together, an egregious amount of models, egregious amount of complexity. So complicated, they didn't even use it after they won, or like the Netflix didn't even use the winning solution, right? And that's why I call them monsters. And the same thing can be found in many historical Kaggle competitions that were won with hundreds of models all ensembled together in multi-layer stack ensembles that were very complicated, basically. And basically, most people shied away from this. Most systems shied away from this. It's kind of like, this is impractical. It's so expensive. It's so complicated, so bug prone, things like that, right? But my question kind of was, can we tame the monsters? So can we make them reliably performant and stable for various data sets, assemble them without need for expert knowledge, train them in a reasonable amount of time and on a wide variety of hardware, enable the flexibility to satisfy the user constraints, and most importantly, hide all of this complexity behind an elegant API. So AutoGluon strives to achieve these goals. AutoGluon strives to tame the monsters. So how do we go about this? So we have a bunch of different model varieties. So basically, we take all the best of what is available in open source, we slam it all together, and basically we can train all these types of models with all the different types of hyperparameters for them. And we have like good configurations basically for them that perform well. Then we do something called model bagging, where basically we take the data, the input training data basically of the user, and then we split it up into different folds where we train models for each fold, and then we generate something called out-of-fold predictions. Out-of-fold predictions are something that's far more complicated than what I'm going to be conveying through this talk, but you can look this up later. For example, you can go to our paper, the AutoGluon tabular paper, for more details. But basically, this allows us to calculate both a cross-validation score as well as a test score, and bagging generally gets much better results than a single model. So you generally want to bag if you're looking to get the best results. So that's one component. The next is multi-layer stack ensembling, which again is fairly complicated. I recommend reading up on it separately from the tutorial to get a full understanding. But basically at training time, we use these out-of-fold predictions that I had mentioned. to pass as features to stacker models, which is basically models that learn interactions of machine learning models as features in combination with the original features of the data. And this ends up being very, very strong and is what wins a lot of Kaggle competitions. And then we use also weighted ensembling by Caruana et al. Ensemble selection. Yeah, and then at test time, basically, instead of using out-of-full predictions, we just take the predictions of the bag averaged, and this is what it is. And also, if you look at this hard enough, basically, this is a fully connected neural network with a skip connection. It's just that instead of perceptrons, it's, you know, XGBoost and CapBoost and neural networks and all that fancy stuff. So to use AutoGluon, you can use these 3 lines of code and it will serve you quite well. Basically, this is in Python from AutoGluon.tabular, import tabular predictor. Basically, initialize the tabular predictor by specifying the label column you want to predict, such as class. Call .fit, specify your training data, either a pandas data frame or the path to the file. Specify your preset, for example, best quality, and specify how long you want to wait for the result. And basically, the longer AutoGluon trains, generally the better it'll be. And then finally, you just get your predictions via predictor.predict, test.csv. There you go. That's it solved, basically. And so this is like a drop-in replacement for like what you could have done with, say, like XGBoost or random forest or a neural network or whatever, right? It's like it applies in the same scenarios. And you don't need to worry about hyperparameter tuning it or anything. You just say best quality preset and that's it. Okay, so a little sneak peek into something I'm going to be talking about later. Can AutoML win a live Kaggle competition? So in January 2023, something really interesting happened. So basically, there was a competition with with like 680 competing teams, and the first place solution actually used AutoGluon. Now, it wasn't purely just those 3 lines of code, and that was it. It was they did custom feature engineering, and then they passed that into AutoGluon, and that got first place in the competition. And what's notable is from top Kaggle grandmasters, such as the Devastator here, they mentioned that they had never seen that before. Basically, they had never seen an AutoML system take first place in a competition before. And so this is very interesting, right? You know, as a field that wants to make tools that are easy to use, but also effective, I think that this is like a really good high bar, basically, to think about, right? Is can we actually compete in these competitions with these tools? So anyways, let's see. Because with AutoGluon 1.0, which was released in, I think it was October 2023, so basically last year, a little bit after last AutoML conference, we had some pretty huge improvements, which I will cover. So first of all, multi-layer stack ensembling, which is like the key ingredient to AutoGluon, can lead to dramatic overfitting in some scenarios. This is a very complicated topic. If you want to learn more about it, basically, we talked about it more in last year's talk. So you can refer to that video. But basically, the way we can fix it is we implemented something called dynamic stacking, which basically we have a holdout data, which we then fit the stack ensemble, and we check the individual components of the stack ensemble, see which of them overfit, and then based on that, we can adjust how many layers of stacking we fit to basically avoid this tricky problem that we haven't actually solved yet inherently. And huge credit to Leonard Perker, who's in the audience. He's the one that implemented this. So congrats to him. Hopefully we'll have a paper someday. Yes, and by the way, if any of you are doing like research on tabular data or are interested in something, this specific topic, I think, would be a very important area if you want to try to improve the state of the art. Yeah. And then, yeah, basically, once you figure that out, you refit on the configuration that you found did best on the holdout. Yeah. So next up is hyperparameter optimization. It's the thing that AutoGluon didn't do. So surprisingly, AutoGluon achieves strong results without hyperparameter optimization. And by default, AutoGluon just trains 13 models with fixed hyperparameters. It's nothing too fancy. Does HPO help? Yes, but it's often better to spend time on other things such as cross-validation, stacking, etc. But can we do better? So incoming is tab repo, which is pre-computed results for tabular ML. It's also a paper at this year's AutoML conference, so feel free to stop by the poster session if you want to learn more about it. But basically what we do is we save validation and test set predictions for 200 OpenML datasets, 3 folds each, with 11 model families and 1,530 random bagged model configurations per task for a total of 7.75 million fitted models. And we also get results for 6 AutoML systems. And so what we can do with this is we can now use all this information that we saved and query it. So basically, instead of having to fit a multi-layer perceptron with a certain hyperparameter setting on a given data set, you can just ask what the result would have been, and it will just fetch it for you because we already trained that model. And not only will it tell you like the accuracy, the training time, the inference time, it will also tell you this is the exact prediction probabilities that it gave for every single sample of the data. And by the way, just so that I don't forget, basically this is a joint work with David Salinas and myself. And you can see the reference here. That's the full paper name. And so basically, validation prediction probabilities we can call VPP, test prediction probabilities we can call TPP. Long story short, basically we can use this information to fit weighted ensembles without having to train the models again. So we can say, oh, what if on data set A, I wanted to train model B and model C, and I wanted to fit a weighted ensemble, then what would have been the test score? Well, here you just ask tab repo to provide you like that information. And tab repo, not only will it be able to tell you what the prediction probabilities of those models were on that data set, we even have logic that implements the weighted ensembling logic too. So you can just say, evaluate ensemble, these are your models that you want to ensemble together. This is the data set, it'll return you the result. And so what you can do with this is pretty interesting. So we can use pre-computed results to find good portfolios. So starting from an empty list, simply select the best model to add to the existing portfolio that achieves the best average test score on the training data sets, and repeat n times for portfolio size n. We can evaluate via 200-fold cross-validation, and this training time reduces from days to seconds because we aren't actually fitting the models anymore. And we find that this portfolio actually outperforms AutoGluon. And AutoGluon was the state of the art, which means this is a new state of the art. So, and also this thing doesn't even use stack ensembling. That thing I said was like super powerful and like AutoGluon used to like be the state of the art. This portfolio that we just generate here actually is better than AutoGluon, even with AutoGluon stacking, and this doesn't do stacking. So, and further, we can do tons of ablations because again, we're just simulating things very quickly. We don't need to refit models. We can like very robustly find many, many different portfolios that beat AutoGluon basically with different amounts of training data sets, configurations per family, portfolio configurations, all this different stuff. And another interesting one is model family presence. Basically, this is like the proportion of each model family that is part of the portfolio as it grows, which is an interesting one. You can find that in our paper. And so putting everything together. So what if we took those results that we got there with that portfolio plus dynamic stacking, and we added stacking to it? So basically that thing that beats AutoGluon without stacking, what if we stacked that thing, basically? So this is what AutoGluon 1.0 is. So the results is what I believe to be the largest leap forward in the state of the art of tabular methods in over 4 years. It has a 75% win rate versus AutoGluon 0.8, which is the previous release, with a 7.4% relative loss improvement. It has an 82% win rate versus the second best method and 10.8% relative loss improvement, and a 63% win rate versus the Oracle combination of all prior systems. So basically, if you were to take Oracle, the best result achieved from on every other system on a given data set, AutoGluon 1.0 would have won 63% of the time. Also, 100% win rate versus XGBoost, and 90% win rate versus LightGBM, with the caveat this is with the AutoGluon default params of those models, but still pretty high. And in terms of the AutoML benchmark 2024, so this was the original results with AutoGluon 0.8 in the paper. And then with AutoGluon 1.0, we go from an average rank of around 3 to an average rank of around 2, which is a pretty large improvement. And then further, when we talk about the Pareto frontiers of, say, like accuracy and inference speed or accuracy and training time, we can also see the impact here. So this is what the Pareto frontier looks like for accuracy versus inference throughput without AutoGluon, basically. And then with AutoGluon 1.0, these are just different presets of AutoGluon. So basically, like the one at the top that has the highest but is like a slow in inference is AutoGluon best quality. Then there's AutoGluon high quality, then AutoGluon high quality with an infer limit set, a smaller infer limit set, an even smaller infer limit set. Infer limit basically being logic that limits or like restricts AutoGluon to having at least this much throughput of like inference rows per second. Yeah. And another thing is this is AutoGluon 0.8 with best quality. So not only does 1.0 get much higher accuracy, but if we equalize for accuracy, we actually get far faster inference speed. Similarly, we can look at accuracy and training time. So basically, with AutoGluon, we're able to, in 5 minutes, get a very, very strong result. So with just 5 minutes of training time, we can get a very accurate model. But if you go longer, you can get even more accurate. We also got into 0 failures in 1040 tests as of AutoGluon 1.0. The funny thing is with 1.1, we actually have some failures now because we fixed a bug. And because we fixed a bug, that made failures happen. It's funny how those things work. But yeah, generally speaking, it's quite stable. Another ways to visualize is like rescaled accuracy. This time as a box plot. You can see that the dynamic stacking and tab repo portfolio has greatly increased the consistency of AutoGluon. If you compare AutoGluon 1.0 with 0.8. And similarly with champion loss delta, which is basically the percentage more error or the percentage less area that the champion method has than the system shown here is what this means. And I'm going to start speeding through things a little bit to not take too long. But another thing is that Chatbot Arena, if you've heard of that, it has very nice comparison plots and figures, and they actually open source the code for it. So I decided to just apply that to like the AutoML benchmark results. And we can actually do things like calculating ELO ratings for all tabular ML methods by doing pairwise comparisons. We can also, do, for example, average win rate against all other models. And we can do pairwise win rates as well. So basically, these are the same plots that are in like Chatbot Arena, but we can apply these to AutoML methods as well. So now going to Kaggle. So right, I just said a bunch of results in terms of comparisons on like, AutoML benchmark, but I think the real thing that matters is in terms of basically, are people actually using it and do they find it useful? And basically, is it holding up against the very, very best? And I think the very, very best is generally can be found on competitions. So in the first competition of 2024, where AutoGluon 1.0 was available, early on in the competition, basically the top, I think, 11 notebooks were all using AutoGluon, which is pretty interesting. And at the end of the competition, it was used in the second place solution out of 3,777 competitors. And similarly with the second one. And so basically in summary, I basically did I tracked this. So in 2024, Kaggle has had 16 major tabular ML competitions as of September 6th. And with an average of 1,500 human teams, AutoGluon had podium finishes in 13 out of 16 of them. So basically, it's to the point now where AutoML systems are very hard to outperform when not using AutoML systems, which this is the first time, because you remember in 2023, people were saying they had never seen an AutoML system place in a competition before. Yeah, so basically, it turns out XGBoost is not all you need. Yeah, and you can find the source of this in awesome.md, where all of these links are the write-ups for all of the solution posts, basically, for people on Kaggle, for all of them. Yeah. And I think right before I do mini Q&A, I'll do a couple things on sneak peek to what AutoGluon 1.2 is doing. So we're going to do 3 times faster inference speed, basically via model pruning to the stack ensemble, tons of stuff. 5 times faster training via parallel model fits on large machines. Kudos to Lana Perker. 5 times faster install. If you haven't heard of UV, it's kind of like magic. It's pretty cool. Allows for 1-minute installs on Colab. Python 3.12 support. Bunch of cool stuff. Callback support. Basically, if you want to take control of AutoGluon's execution logic and have it fit whatever models you want in whatever order and tell it to stop whenever you want, you can now add callbacks to it and just define your own custom logic, basically. Yeah, lots of things, basically. And then there's like tab repo 2.0 also, where basically I want to improve the state of the art of tabular benchmarking consistency. Yeah, but I'm not going to go too much more into it because I think we'll run a bit short on time, but I'm happy to start a mini Q&A. Anyone has any questions? All right, then.
Maybe I have one.
Oh yeah, sure.
How will the results of tab repo now affect how AutoGluon works? Or will you keep them separate as 2 lines of projects?
So basically how tab repo works is that we learn a portfolio in tab repo and then, yeah, basically we learn a portfolio in tab repo and then we apply that portfolio to AutoGluon. We like choose a portfolio that we think is reasonable in terms of its accuracy versus like inference throughput on average. And then that becomes like the default in AutoGluon. And so the idea is that as tab repo expands and adds new methods and new data sets and new techniques to it, we would find better and better portfolios or strategies. And then we would apply those basically yeah, basically we would apply them to AutoGluon. So it's like tab repo will enhance AutoGluon. And so whenever we enhance tab repo, it would enhance AutoGluon. Yeah. Okay, cool.
Thanks for the presentation so far. You mentioned that instead of hyperparameter optimization, it's better to spend your resources on other things.
Mm-hmm.
Did I understand correctly that if you spend it on other things, the only thing you can do is get a better informed decision on which of those 13 models you have to choose? Or did I misunderstand something?
So for example, the things that we were doing, so like, for example, you can do cross-validation and bagging, which is a more expensive way of training models, but basically it leads to less overfitting and will lead to generally better accuracy. So that's like one example. The other thing that we did at the time was we did repeated bagging, where basically you can bag once, but then you can just bag again on different seeds, and that will like slightly improve the results. We don't actually do that anymore by default, just because now with the portfolio at like 100 models, it would be a bit ridiculous to like, you know, repeated bag the portfolio of 100 bagged models and then stack ensemble them. So we don't do that, but like, but yeah, so like it was just like 13 models though. That was what it was for years. It was just like train 13 models with fixed hyperparameters on every single data set and then ensemble them together and like with a stack ensemble, yeah. Okay, cool. Then I think we can go to our next presentation.
Thanks a lot, Nick. So far we have seen some of the work that was happening in AutoGluon on machine learning for tabular data, but now we'll talk about another big data modality that is quite important, that is time series forecasting, and about our recent work on pre-trained models for time series forecasting, what's happening in AutoGluon on that front, and also what the future of AutoML might look like in this space. So first, kind of as a short overview, what is time series forecasting? So far, we have looked at tabular machine learning problems, which is essentially regression and classification. And time series forecasting is another quite important domain that comes up in many applications in the industry and like sciences, where we have to forecast the future given the past. Essentially, time series show up whenever we have something that we measure over time. One example would be energy demand, where let's say at different points in time, you want to like measure how much energy is being consumed by different customers of your energy company. And then you want to forecast what will happen in the future to make sure that you can satisfy the demand for what will come in the future. There are also lots of other cases where this happens, maybe in retail, where you want to make sure that you have enough items in stock for the sales. Maybe in finance, you want to forecast the prices of some assets to make sure that you can make good trades. So this comes up whenever some things are changing over time, and we want to figure out how they will change in the future. We quite often care about not just a single point forecast, but we care about a probabilistic forecast, which means we want to reason about the ranges of possible outcomes of what will happen in the future. So, for example, like is a simple case where we care about point forecasting, we might say, what will the sales be tomorrow? Maybe our machine learning model will say we expect to sell 200 units tomorrow. This might not be enough if you want to be ready for maybe the worst case or the best case. Maybe you want to have a prediction which tells us something about the range of the outcomes, and it will tell us, hey, there is a 80% chance that our sales will be between 190 and 220 units. And these kinds of decisions can be taken into account in our decision-making system later in the models. But essentially, it's all about kind of modeling the conditional distribution, what will happen in the future, given the past values of the time series. And this is the type of problem that we aim to solve in AutoGluon time series. So I won't go into too much on details about how to use AutoGluon time series. We'll mostly talk about what's happening under the hood and how things work. But it's anyway good to kind of like see that it's a similar API to what we have seen for AutoGluon tabular, where we have to specify our forecasting task. Maybe we want to say how many steps into the future we want to make the predictions. We want to maybe specify some other things, which evaluation metrics we care about, which quantiles we want to predict. We provide our training data, and then we make the predictions, which then tell us what will happen in the future and generate this quantile forecast. So very simple API, but as usual with AutoGluon, our goal is to hide the best possible machine learning models, the best possible approaches behind this very simple API that will get us to the best possible predictions. And of course, all the interesting stuff happens in the fit method, where the real AutoML comes to play. So we follow a very similar recipe to what happens in AutoGluon tabular, where we have quite a large portfolio of models, kind of combining the best of open source out there. And we train all the different models and learn how to combine them with an ensemble. As for the actual models, we combine lots of different approaches, starting from simple statistical models and maybe even baseline models, going to more complex ones, such as machine learning methods like LightGBM or CatBoost, and also deep learning models from libraries like GluonTS. For the ensemble strategy, it's something very similar to what we have in AutoGluon tabular, where we rely on a weighted ensemble. And this again here doesn't rely on hyperparameter tuning. The idea is essentially to have just a very good representative portfolio of the models, find a good way to combine it, and this recipe works really well in practice. Now I want to take a minute to go into more detail about which models we have available in AutoGluon time series, kind of see what the advantages and disadvantages are of the existing traditional forecasting models. And then we'll move on to discuss how this will, is already changing now and will change later in the future as we move to new classes of models. The first type of models that we often deal with in forecasting are so-called local models or statistical models or econometric models. Maybe you have heard about the names like ARIMA, ETS, or theta. And the idea here is quite simple. You have some very basic parametric model, which maybe has a dozen or even a few parameters. And you fit a separate model for each time series in the data set. So for example, the ETS model, it has some parameters for the presence of a trend in the time series, maybe something for seasonality, where you have these repeating patterns that kind of look like a sine wave, and also telling you how the things change over time. You have a few of these parameters in these simple models, and you fit them for each of the time series that you have in your data set that you want to forecast. So for example, if you want to forecast 1,000, the sales for 1,000 products in your catalog, you would have to fit 1,000 models. These models are quite simple. They have been used for a very long time, so we understand their limitations and their strengths quite well. Surprisingly, even despite their simplicity, these models happen to be really really strong as baselines quite often. And maybe if you have limited data or you have lots of missing values, these models could be might give you very strong results. But they of course have the limitations that are related to first their low flexibility, which happens because these models only have a few parameters. They cannot capture complex patterns. We usually rely on these very simple properties of the time series that are present in there. And also another big disadvantage is their slow inference time, because each time we want to forecast a new time series, we have to fit a new model. That takes time. This ends up being quite slow, quite clunky, and in practice not so comfortable to deal with, especially in production setting where you have to keep forecasting over and over for lots of different time series. And having seen these limitations of the local models, people in the last decade have started to switch more to machine learning approaches and see how we can use all these cool advances in deep learning, machine learning, to come up with better forecasting models. And one big class of methods that came up in the last decade are so-called global models that are usually based on some machine learning or deep learning architectures. And the idea here is, instead of fitting a single model for every time series in the data set, like we did before, to just fit a single global model that we will use to forecast all the many different time series in our data set. So maybe if you want to have, if you have like thousands of products for which you want to forecast the sales, you would fit a single neural network that, looking at the history, gives you the predictions for the future of these time series. And you estimate the parameters of these models on a large training data set available to you. These models are much more flexible because neural networks, as we know, are quite flexible, so they can capture quite complex patterns. They also faster at inference time, because every time you want to make a prediction, you don't have to refit a new model. You just have to make a single forward pass through a neural net, and your predictions are there, which is, of course, nice compared to local models, but again, comes at a cost. First, we have to train these models for each new task that you have. So maybe, if you have one store for which you want to make the demand forecast, you will train one model. Then, if a different store has different products, they might need to train a different model. And in different domains, you will have to train all the different task-specific models, which is, takes time. And of course, it also is data hungry, because we have to actually get these data sets to train these models. If we only have a single time series that you want to forecast, and we don't have much data to train these models on, it's very likely that you can fit this flexible neural network with lots of parameters on just a single time series in your data set. So it kind of places a pretty large constraint on your data sets, where you will only, they will only work if you have lots of training data available and you have time and patience to train all these models. So we have seen these two main classes of models that existed so far, local models and global models, that each have their limitations. And looking at this state of things, where each of them have some problems, people started asking questions. Maybe it's somehow possible to look into some new directions for new inspirations to come up with new models that don't suffer from these issues. Maybe we could have some single model that doesn't need to be trained for every new data set that comes up for us, but also performs well on new unseen time series. So, of course, it's kind of inspired by large language models and the success in the field of natural language processing, where, if you want to do different tasks related to text, you usually don't have separate model for each specific task. Very often, you can take an off-the-shelf pre-trained model, just give it to your data, and the model will give you reasonable predictions that usually are quite good. So the question is, can we do something similar in the world of time series forecasting, where we will have one large, maybe not so large, pre-trained forecasting model, maybe trained in a large collection of data sets that will allow us to generate accurate forecasts for time series in a zero-shot way. So being fast at inference time and being accurate at the same time. This is, a lot of people have been asking this question the last year, and there have been different answers so far. The first thing that people have tried, of course, inspired by the success of large language models and in the NLP domain, is just to look at existing text-based LLMs and see if they can somehow be repurposed for forecasting. So essentially, people were thinking, these LLMs have been trained on all of humanity's knowledge. Maybe if we can ask them nicely enough, they will tell us what the future will look like. And people have tried different ways of doing that. This very simple ones here shown on the left essentially convert the forecasting problem into a text generation problem, where maybe you can tokenize your continuous time series values into tokens that you can pass into a model, such as LLM time, and just treat it as a text continuation issue. You can also try to add some context around it using text, such as in prompt cast, where maybe say I have such and such time series measured over this period of time, and I want to forecast its values into the future. Besides just treating LLMs as these text generation machines, people have also tried to slightly tweak their architecture. And again, starting from architectures that were pre-trained on text, turn them into forecasters by maybe adding some new embedding layers, fine-tuning the input or output layers, essentially doing some small tweaks and turning that into forecasters. This is a reasonable thing to try, but in the end, it didn't work so well. And it has a few reasons. The first one is that these models that we use for text are actually huge, and they're super expensive and slow to run. We often need multiple GPUs that are very good. So it's not really it's not worth it for many of these forecasting use cases. The performance that these models had wasn't great in terms of the forecast accuracy, because as you can imagine, text and time series are actually quite different. And ability to generate plausible sentences does not necessarily translate to the ability to generate accurate time series forecasts. And we also had the problem that these models, so especially these approaches that you see here on the right, where we have to do some fine tuning or tweaks to the model, they would often require some task-specific prompt tuning, prompt engineering or fine tuning, which essentially means that, this whole promise of a zero-shot forecaster that can just off the shelf give you a good forecast is not really that's not what's happening here. Because if for each data set, you have to, again, retrain the model, do prompt engineering, it's not really a zero-shot forecaster, so it's not so convenient as you would imagine. And looking at these limitations of the approaches that people have tried, we have thought about a slightly different one, which also uses large language model architectures, but repurposes them to forecast in a different way. And we have explored this way of turning LLMs into forecaster in our paper called Chronos. The idea here is essentially to treat time series forecasting as a next token prediction problem, but without even looking at the pre-training data sets, without looking at models that are used exclusively for text generation, but rather treating them as forecasters from the very beginning. If you look at it on a high level, then both time series forecasting and language modeling, they are kind of similar problems. In both cases, you have a sequence, and you want to kind of answer the question of how will this sequence evolve in the future. In case of language modeling, the sequence is a text, so it's a series of tokens, which maybe combine multiple letters or words into one. We have the discrete tokens that go into the future. And in case of time series forecasting, the elements of the sequence are the continuous values of the time series, which of course is quite important and also quite different from text generation. These models, the way have been developed for NLP, always heavily rely on this assumption that your sequences consist of these discrete tokens. So whenever you have some sentence, you turn it into these discrete token IDs using the tokenizer, which essentially tells you maybe each word in your sentence corresponds to some integer from 1 to the vocabulary size. The model sees the sequence of these integers and then generates future values of these integers corresponding to the token IDs. And this way we can generate the text. In case of time series forecasting, it's not so obvious how we can turn the forecasting problem into this discrete sequence generation. So, but if we were able to do that, that would be essentially the solution to our problem. If we, maybe put it differently, if we are able to formulate the time series forecasting as a problem where we have seen some past discrete tokens and we have to predict what the future discrete tokens will be, we will immediately be able to use all of these LLM architectures as a forecasting model. And this is essentially what we have done in this paper in the Chronos architecture. Turns out there's a very simple approach that you can use to turn the continuous valued time series observations into discrete token IDs. First of all, you have to scale the time series because, as you would imagine, many time series in the real world have very different scales. Maybe if you're forecasting the population of the Earth, which is in billions, versus forecasting the temperature, which is maybe in tens, it's very different scales, and model somehow has to be invariant to all these different scales of the data. And for that, we can use a simple technique called mean scaling, where we just compute the average absolute value of the time series in the context window and divide all the time series by this value. Once we have done the scaling, we can just put the time series into the bins. And here we consider a very simple approach that surprisingly works well in practice. We just look at the interval from -15 to 15. We divide it into equally sized bins, and we see into which bin each of the time series values falls into. So essentially, if your time series value falls into the bin number 2400, it means that this time series value is represented by the integer 2400. And by just defining this procedure that we see on the slide, where we first scale and then do quantization, we end up transforming our time series that is originally a sequence of continuous signals into the sequence of discrete integer token IDs that can be processed by the LLM. And once you have done this transformation, everything else just follows naturally, and we can use large language models or like any language model architecture as is. As you remember, with LLMs, typically the input to the model is just this sequence of the context tokens, which we obtained in the previous slide with scaling and quantization. Then what the model does, it outputs the distribution over the next token in the sequence. So in this case, let's say we are in the training phase. So we know both the value of the context time series, we have seen it before, and we also know the next value in the sequence. All we have to do is just convert so we first convert the context values into the sequence of tokens. We pass it through the LLM. The LLM gives us the categorical distribution of the next token in the sequence. We then see, okay, what is the actually observed next token? We see the log probability of this next token in the sequence, and this log probability becomes our training objective. So we want to maximize the log probability of the data in our training set, or in other words, we want to minimize the cross entropy. So exactly as the LLM architecture, and the main important difference here is that our data is not the text data anymore, but we rather be obtaining it with this scaling and quantization approach from continuous value time series datasets. After we train this model by optimizing the cross entropy loss, we can again use these language models for text as if it was a text generation task, where we can just autoregressively unroll the sequences. So we give to the model the past time series values. The model generates the future time series values one by one. We do this multiple times, and we get a multi-step ahead prediction for the model. So we have one possible future time series value. This time series value, we can then turn this sequence of tokens, we can then turn back into the time series value by first looking up which token ID corresponds to which time series value. We do the scaling, so returning the time series to the original scale, and this way we have a one time series trajectory. If we repeat this procedure multiple times, we end up with multiple trajectories, and from these multiple trajectories we get a probabilistic forecast. So we can compute the mean of these trajectories, we can compute different quantiles, and this is essentially all we need in a time series forecasting problem. So in short, the Chronos framework was like a pretty small, but very, in the end, very effective observation that we can just convert the problem of time series forecasting into this next token prediction problem by scaling and quantization, and we can train existing LLM architectures to forecast time series this way. What's important here is that, of course, like it's not just, so this idea in itself is quite simple, but there's also another very big component of training these models, and that's the data. Because if you don't have the data, no matter how good your idea is, you cannot train anything, you cannot forecast, you cannot do any forecasting. So a very big portion of this project was, of course, also not just finding these good representations for the data, but collecting the data itself. And we ended up collecting quite a large collection of open source time series datasets with about 890K time series in total, with almost 84 billion observations from different domains, from retail and energy to finance and economics and traffic, lots of different ones. This is pretty large as far as time series datasets go, but it's still nowhere near as close as the datasets used in natural language processing for text-based models. So we wanted to see if we can push this even further and maybe explore some ideas how to increase the diversity and quality of the training set. And for that, we came up with two strategies for data augmentation. The first one was about was what we call TS mix, where essentially the idea is to sample random number of time series from all these different domains, and then take random linear combinations of these time series in the data. So you can see in the figure on the right, on the left here, maybe we see 2 time series that have different seasonal patterns. So this one on top has slightly longer seasonal pattern. The one below has a shorter seasonal period. If we combine them together, we get a new time series with some new seasonal pattern. Maybe we have another one which has a trend. If we add it to the previous time series, we now have something that has both the trend and the seasonality. And this way, by taking different combinations of different time series from different domains, we effectively increase the diversity of the data set even more. And the model ends up learning more patterns and seeing more different combinations of what can happen with the different time series data sets. And in addition to this strategy where we combined real-world time series, we also augmented the training set with some synthetic data where we use Gaussian processes with different kernels to generate new different time series. There are lots of kernels that people have explored in the literature, from, again, linear kernels, which is kind of result in a trend in the time series, to periodic ones, and that result in seasonality, or RBFs, where you maybe have some bumps or events in your time series. By sampling the different kernels, generated from the resulting Gaussian processes, we end up with the synthetic time series that we can, again, throw into our mix of training data, resulting in an even larger training set. And once we generated all these different training sets with different augmentations and synthetic data augmentations, we trained 5 versions of the model with different model sizes. And again, one of the hypotheses that we wanted to verify in here is whether larger models work better. And spoiler alert, yes, actually, like the larger the models, the better it worked. But the idea is essentially like that with different model sizes, you can get different trade-offs between the speed and the accuracy of the forecast that you get in the end. At this point, it's probably worth mentioning that there also have been other works in the field of time series forecasting and pre-trained models specifically. So since we open sourced the Chronos model, a number of other ones have also been made open source, sometimes through an API, sometimes actually the model weights were also put on Hugging Face or open source. These models usually take different approach from Chronos. So in Chronos, we essentially, if you think about the modeling framework, we kind of build very heavily on what has been done in the NLP community and in large language model architectures, where it's just about kind of the data representation, data collection, and data pre-processing, which was the different part, but the internal part with the LLM, data loaders, training, etc. It was all existing infrastructure, which made things very scalable, very easy, and also convenient to combine with existing code. But here people have often tried to go for time series specific designs with some very special design choices and architecture choices that we will see also work quite well, but in the end not end up working quite well as the forecasting model, as the LLM-based models we have seen so far. Okay, I think maybe I'll move a bit faster here. So essentially, we did some evaluation for the models. We comparing both the many different pre-trained models, everything that was open source at this point, task-specific models, local models. And this is pretty large table, pretty large figure. You can see the details in the paper. But the main takeaway that we what we have found in practice is that the Chronos models working in zero-shot way, so without any dataset specific fine-tuning, just we take a data set, give it to the Chronos model, no fine-tuning, just zero-shot prediction. The accuracy of these forecasts ended up being almost as good or sometimes better, sometimes slightly worse than the best state-of-the-art models for these data sets. So essentially, lots of other things like traditional statistical models, ETS, ARIMA, etc., they were consistently worse. And among the very best global models that you train specifically for each data set, where you have to train them from scratch, spend a lot of time on that, they in the end had comparable accuracy to Chronos. So this was a pretty big result, which essentially showed us that this recipe of just pre-training on lots of data and combining lots of pre-training data with a large transformer model was allowing us to get very accurate zero-shot forecasts that generalize to new unseen tasks. This is very encouraging news, and maybe we are now actually at an AutoML conference, so you might ask, well, why do we even need AutoML? It seems that this recipe here will just work. In the future of forecasting, at least, we will have one big pre-trained foundation models. Maybe in NLP, we'll have to add more data, increase the model size, keep training, over and over. But then we just have one model, and we won't need any AutoML. I actually think it's not the case, and maybe I'll try to convince you that this also won't happen in the future. And even in this world of large pre-trained models, we will still need AutoML, and there will be a lot of room for innovation on the AutoML side. So first, like the main reason why I'm saying this is because these pre-trained models like Chronos, even though they are quite large by the standards of forecasting models, they're still tiny compared to LLMs that, that are hundreds of times larger, maybe thousands of times larger, a lot more parameters, a lot slower, a lot more expensive to run. But if we, even if you look at a single model, because it's so cheap, we can do lots of different things with it. We can run it many times. We can see how it performs in the data. We can apply techniques like, of course, fine-tuning. We can also try different pre-processing techniques on the data, which will result in different, results for the model. We can do calibration, conformal prediction. All of these things are kind of like AutoML, even around the single pre-trained model. Because it's so small and so cheap, we can do all of these things. And, of course, it's not just, probably won't just be a single pre-trained forecasting model. I think we'll have a lot of different forecasting models. And then we have a lot of these different models. What can we do with it? Well, we can ensemble it, we can stack them, we can boost them, we can do all of these different things in kind of this huge search space of different, pre-processing, adaptation, and sampling steps. We have a large portfolio of different pre-trained models. And, to kind of find the best pipelines in here, find the best possible combinations, we will have to use AutoML. So very likely, even like in this space with pre-trained models, and AutoML will still play a very important role. Yeah, so something about the challenges, but I think, we can like move on to the next part about forecasting. So just like as a short summary of what we have seen so far, we have seen that pre-trained models can be really good at zero-shot time series forecasting, resulting in very accurate forecasts without any data-specific training, which kind of changes the paradigm on the one hand and makes it like very easy to just take these models off the shelf, use them for prediction. Chronos is one of these models that ended up producing like really good results in practice, but there still remain a lot of open questions. So even as people work on new models, there's a lot of stuff to do in the AutoML space about surrounding these models, how to combine them, how to tweak them to get the best possible performance. At that point, thank you, and we can move on to the next part.
Okay, so hello and welcome again, everyone. So my two colleagues so far, they laid out the today and also the tomorrow of AutoGluon and specifically what we are looking at in the team. I will take a different route. I will actually be talking about where we think the future might be and what steps we're taking towards that. So my talk will be a little different in flavor as well. So I will not be talking about the techniques that are already there in AutoGluon or things that we have implemented. I will rather, in the spirit of this being a tutorial, I will give a very non-exhaustive, I will probably say this again, survey of things that are being done in this field of automating AutoML, or maybe the goal of taking AutoML from 3 lines of code, as AutoGluon already is, to 0 lines of code. And then I will relate a bit about our thinking there and what we are doing in this direction. So I believe we have all seen a version of this slide, the data science pipeline, a conceptualization of how a data scientist works. So when a data scientist is given a problem description and raw data, they first perform some element of task analysis and planning. So they understand what they're supposed to do. They translate the business problem, if you will, into a machine learning problem or a data science problem. Then, of course, well, these two boxes there are called different things, but they clean the data, they wrangle the data, they generate features from that data in order to be able to invoke a machine learning system. Then they invoke that machine learning system, and then they deploy the model in production. They monitor it maybe, or they maintain it somehow. The scope of AutoML in this whole pipeline has always been referred to as, either the model building or the feature engineering parts. And well, I guess it surprises no one here that with the advent of large language models and their so-called human-like reasoning abilities, the question has risen that, can we broaden the scope of AutoML? So go from AutoML to something like an automated data scientist. And broadly, I will divide the attempts at answering this question into two categories. One will be about automated data wrangling and feature engineering. So maybe the things that were already there for the last few years, I will briefly talk about some attempts already and what are some of the open problems there. Then I will go to the second step of a broader problem description, actually getting an agent that can autonomously look at a data science task and try to come up with a solution to it. Maybe the second box also subsuming the first of feature generation and data wrangling. And as I said in this talk, I will give a very brief overview of how people have approached this problem before in both automated feature engineering and then automated data science with LLM-backed agents. Again, this will be non-exhaustive, so if this is missing your work, please also bring it up in the questions. Then I will move on to what we will be calling AutoGluon Assistant. So this is very early work, taking its baby steps that we're working on here in the team about sort of bringing these elements together into an autonomous data scientist. And we'll see how that works. So problem description of this first part, automated feature engineering at a very high level. Let's say we're given an input of some tabular data sets. That's probably the best way to think about it. Or you could call it like a relational database captured at a certain point in time. And we are also given some other metadata and perhaps some, let's say, abstract knowledge or a description of the task to be solved. I think a great way to think about this is to think about a Kaggle competition where one gets a collection of CSV files and also about a one-page or two-pager document describing what to do with those files. Right? And the objective here is you may or may not use large language models to do that, but we want to generate another single table that we can just feed into a predictive model. And I think we should all think of the predictive model as AutoGluon. And maybe along with some other metadata, and that we can think of as the parameters that you would use to call AutoGluon, right? And anything that happens in between that we get from this collection of CSV files, this maybe description of the problem, we will call automated feature generation. So some works that have already, I think, are somewhat mature in this field. I'll start with citing OpenFE first. So OpenFE is this single table input and output, I think is the best way of talking about it. Automated feature generation framework. So it does not use LLMs. It is rather, it uses a very large bank of unary and binary operations on the different columns of an existing table to come up with a very large set of candidate features for the task. And then it evaluates these candidate features, which is by then a very large pool, using some AutoML inspired heuristics. And this one can think of, for example, what they do is they use successive halving so as to not evaluate all of the features on all of the data set, right? That would just take an prohibitive amount of time. What they do is they evaluate some of the features on just smaller parts of the data set. And they do this with something they call feature boosting, which is they don't add the feature to the existing set of features at every pass. They rather add the feature to the outputs of a base predictor and try to see if they can improve the predictions like that. And they, after narrowing down the candidate features, they evaluate these features again with a random forest feature importance type mechanism and output what comes out. There's a very good mature implementation in the given link if you are interested in this. And there are, of course, few other alternatives if you'd like to try them out to this single table input and output problem that we are not mentioning here. But then we should move on to probably, given our problem description, a second family of automated feature generation algorithms where the input is not only a single table, it is multiple tables along with a schema description of how those tables are connected together, right? So again, back to the relational database example, we don't only have a single table, we have different tables. One of these tables is interesting. It contains a target column. It contains essentially the task to solve, and the other tables should be joined to this table, perhaps, right? And this, probably the most popular baseline algorithm here is deep feature synthesis. And deep feature synthesis, what it does is it uses essentially either directly joining the other columns from other places in the relational database, or it uses rollups where appropriate to use the schema of the database to bring everything together in the single table, right? This alone forms the deep feature synthesis algorithm. Then there are other approaches that the authors propose for reducing dimensionality of the problem further before feeding it into a predictive model such as AutoGluon. But if you would like to just use the multi-table feature generation algorithm, a good implementation is available in the feature tools library, which is also open source. I would like to mention some work by colleagues at AWS about not only defining, let's say, the problem, but also coming up with like some benchmark data sets, some benchmark evaluation metrics for learning on relational databases, because we were also chatting just now, and also we saw it in the SAP presentation. This is a very nascent field. A lot of common tasks, common definitions of tasks, common data sets, benchmarks they're missing. So in this work, for DB-Infer, the authors propose a comprehensive benchmarking framework, some data sets and evaluation metrics for relational database-based predictive modeling tasks. They formalize the task itself, and then they propose both some approach by first using deep feature synthesis that we just talked about, and then using a predictive model such as AutoGluon to solve that predictive task. But they also propose a formalization of how to translate relational database learning problems into graph neural network-based prediction problems, and work with that to actually solve the problem. And then they compare these two approaches. So a very related work is also defining a benchmark and proposing how to translate relational databases into graph neural network problems is by Matthias Fey and co-authors, called RelBench. But just to give you an idea of what the main insight from this work seems to be, I will just point to the result table from for DB-Infer. The key outcome seems to be that this graph neural network approach seems to work a bit better. This is a little surprising. There is not much talk of how like the computation cost changes, but one can imagine it's a little more expensive. But depending on the task, this two-stage approach of first using a feature generation algorithm to collapse everything into one table and then feeding it to something like AutoGluon, which also features here, seems to also be doing quite fine in some of the data sets. And we can chat about more from this paper in the question and answer session if you'd like. Then we move from the territory of just heuristic automated feature engineering into this, of course, world of LLMs and how to use them to potentially do more than what these machines just do. So how can we use LLMs to generate features of interest for a downstream prediction problem? The first paper probably to address this in detail was Café, which proposed 4 classification tasks using the task description and a textual description of the data set, a single table data set, gave it to an LLM and asked, what are the best features to use? What features can I generate from this data set to use in a downstream prediction problem? Café generates both the description or the reasoning for why the feature is being proposed, along with the Python script to generate that feature. And the paper showed, albeit modest, performance improvements with GPT-4, right? So they also compared 2 large language models, GPT 3.5 and GPT-4, and concluded that using feature generation with GPT-4, even with quite powerful predictive models to solve the downstream task, appears to be working well. For unstructured text features, I can also point to a very recent work called Felix that doesn't work on numerical tabular type features, but on text fields, if you will, and generates features from those, such as like sentiment of a text or such things. And the final work I'll point to is, can foundation models wrangle your data? So not only can we generate features, but we can probably also do things like data cleaning, data imputation, and maybe entity matching between different columns or different tables in the data set. And this paper showed that with 0 to few demonstrations, like in context learning, that one can also do this with LLMs to some success in the context of relational database machine learning. So now let's move on to the second part. Let's broaden the scope. Now that we are using LLMs, can we use them to solve the task end-to-end so as to maybe disrupt the data scientist job market, right? So on the left-hand side, again, we have tabular data files, metadata, and instructions. And out, now we don't want a table that has features. We actually want the full predictions, right? So we want a solution of the predictive task. Again, going by the Kaggle example, we would take the Kaggle competition and we would output the submission file of the Kaggle competition along with maybe the code that was used to generate that. One work I will cite in this area is one of the first to come out, was called Data Interpreter. This is an LLM-based agent framework for data science tasks. And what they do is they break the task down into using the LLM and using, of course, specific prompts. They break the task down into a hierarchical DAG of a plan. So on the left-hand side, you can see here, they first break it down into steps like, I'm going to do data exploration, then I'm going to clean the outliers, then I'm going to do stuff, and then I'll conclude I've done enough, and then I'll output, right? And then they break those things down even further. And they also, in these smaller actions, they can use what LLM people have taken to calling tools. So code snippets or API calls that the LLM can interact with in order to solve the problem at hand. The data interpreter dynamically updates the plan. So this is not static. It usually breaks down for LLM planning stuff that if you just freeze the plan and then try to execute it till the end. And they report quite impressive results for task completion rate. And I should say something about task completion rate here is that, like, if you're working with LLMs in general, they are so unwieldy that at this point in this literature, just getting high success rate, success meaning it ran, is quite impressive. So DS agent incorporates something I will call case-based reasoning. You can think of this as the agent and I'm going to start speeding up here. I hope you'll forgive me, but you can catch me at any point. So the agent has a bank, a database, if you will, of past experiences. And these experiences you can think of as insights that you would find in a Kaggle discussion post forum, right? On this competition, on such and such data, this kind of approach worked. And then at test time, what the agent does is it performs RAG on this database of cases, and then incorporates those to come up with a solution to the task. And at training time, what they do is actually offline mode. They do this, they evaluate, and then they pick the things that worked and also put it into the database. So the agent also gathers experience. A very similar approach was taken by ML Copilot. This is work by Microsoft Research, where they took historical data again, and actually in the previous paper, this was actually Kaggle discussion forums. This was how the agent was seeded, right? And they follow a similar approach. They canonicalize is the word they use. They gather these experiences. They convert it to something like this. My task was to do this, and this was my solution, and it worked, right? And then they store this in a database. And then they also have another process to visit this experience bank and come up with even higher level stuff, right? So like CNN is commonly used for image data sets. So this is another approach that was taken, and there is a very fun Jupyter-based implementation online if you'd like to play with that. With your permission, I will skip ML Agent Bench and move straight to AutoGluon Assistant. So AutoGluon Assistant is our attempt, our very forward-looking project in the team to implement an automated data scientist. Our reasoning is simple. I'll just skip the left-hand column. AutoGluon is great. Everyone on Kaggle is using it. And Kaggle is a great source for prepackaged data science tasks. So can we, using LLMs and AutoGluon, can we come up with, in quotes, an automated data scientist? We build on a very simple flow, incorporating many of these tools that we just mentioned, and we start from a collection of tabular data files. We prompt an LLM to perform some inference on the task to be solved and figure out the very basic things, right? So what's the label column if this is a supervised learning task, and which CSV file does this column exist? And we use in order Café, OpenFE, DFS to generate features for the task at hand. We then, of course, feed everything into AutoGluon tabular, and out comes the submission-ready input file that we can actually send to Kaggle. And let me go to this. Send to Kaggle we did. Actually, during the AutoML Grand Prix over the past 5 months, AutoGluon Assistant was running in secret in the competition. And it successfully ran on all of the Tabular Playground series competitions. It figured out everything it needed to figure out, and it made a submission. Most of those submissions, of course, fell against the very helpful community, as it turns out, of Kagglers who just wanted to post their latest solution so everyone else could also submit with it. But I think in one competition, it really surprised us. In the 4th competition, it actually used features that Café produced to get the 2nd place result. Here's like the 1st place result right before Nick and Leonard just made the final sprint for the 1st place in that competition. And as I said, like GPT-4 Café feature generation and AutoGluon for 12 hours with no human intervention whatsoever came 2nd in the competition. The key thing about the design principles of AutoGluon Assistant is one thing that we take care is we don't really rely on the LLM so far to do any kind of code generation because of the reliability issues that we talked about so far. We just prompt it with very specific prompts and try to elicit very structured output. We ask it simple questions, we try to get the simple answers, and we run that through a very, let's say, pre-configured pipeline of what to do in a data science task, something that resembles, of course, the pipeline shown at the very beginning. We also focus a lot on accuracy, as we do in AutoML in general. We focus on extensibility, so that is how we're trying to build it. So now Cafe is in there, DFS is in there, OpenFE is in there, but we want to come up with other tools, and we're designing things in a modular fashion so that we can pipeline different LLM steps together, and then those can fail over, and that if they fail, like the show doesn't stop. And of course, we're building for AutoGluon first. And that is actually the reason why there are no experimental results on these slides, because AutoGluon, as it turns out, it actually goes quite a lot of the distance of beating you in terms of accuracy. So even if you don't talk to any LLMs or if you don't generate any features, it is actually already doing quite impressively. So we'll get you some results once we start beating AutoGluon tabular. Yeah, so this is looking forward a bit. Yeah, it's taking its baby steps. It was able to compete on Kaggle, but there's a lot to do before we release AutoGluon Assistant. We hope to be able to do that this year, but for more news on that, please watch this space on either GitHub or auto.gluon.ai. And with that, I think we can move to the questions with my co-authors here.